Hi. In next concept, we'll now be just looking at how to approach exponential based equations and inequalities. So for exponential based equations and inequalities, again the idea is pretty straightforward. But let's just quickly first revise the basic properties of exponents. Right, so these are some very basic properties of exponentials which you already know from your earlier classes. So if a is a quantity which is positive and it's not equal to 1, then all these 6 results hold true. So when I say that this is an exponential term, over here a is referred to as the base, and of course, for example, the 0 over here is the exponent. So a raised to 0 will be 1, a raised to 1 will always be a raised to m into a raised to n will always be the same as a raised to m plus n. A raised to m by a raised to n will be a raised to m minus n. A raised to m whole raised to n is the same as a raised to n raised to m, which is the same as a raised to m, and that is also fine. This basic property basically says that if a raised to m, if the bases on both sides are the same, you can equate the exponents. In this property again, this conclusion when that a raised to m is equal to a raised to n implies that m is equal to n again is strictly valid only when a is not equal to 1, because obviously if a is equal to 1, then m and n could be any possible values. So when I say that the bases are the same and therefore equate the exponents, that has the underlying assumption that the base itself is not equal to 1. And of course another basic, when you're talking about negative exponents, so a term of the form a raised to minus m is basically the same as 1 upon a raised to n. Then we can also come up with some properties of exponents which involve inequalities. So for example, again assuming that a is positive, as far as inequalities are concerned, it is important to differentiate between two possibilities. The base can either be between 0 and 1, or it could be greater than 1. If the base is between 0 and 1, then one should observe that for a base which is between 0 and 1, the higher the exponent is, the smaller the value of the output becomes. So for example, if you talk about half raised to 1 is 0.5, half raised to 2 becomes 0.25, half raised to 3 becomes 0.125, and so on. So if you fix your base at half, it is quite obvious that as the exponent increases, the overall value of the operation keeps on reducing. Right? So that's why, just to generalize, we say that if a is between 0 to 1, then the statement m less than l will imply that a raised to m itself has to be greater than a raised to m. That is to say that when you kind of take an exponent on both sides to the base a, the sign of inequality reverses. And conversely, if you have the statement a raised to m and greater than a raised to n, then the way you're comparing the exponents is to say that m itself is less than n. So these properties, for example, can be now used in solving certain exponential based inequalities. So as an example, if I have 2 raised to x square minus x is greater than 1, and I want to solve this inequality, what I'll say is that 2 raised to x square minus x is greater than 2 raised to 0. Sorry. So 1 can be written as half to the power 0, and at this stage I'll say that again you have a statement of this particular form, but the base is half and it is less than 1. So for the inequality between the exponents, the order will get reversed. And therefore x should only take values between 0 and 1. This of course is the idea when the base itself is between 0 to 1. You can have the possibility that the base itself is greater than 1. So in that case, what will happen? So again, and a simple observation is that for an exponent for a base which is greater than 1, as you keep increasing the value of the exponent, the output of the operation will go on increasing. So 2 raised to 2 is greater than 2 raised to 1, 2 raised to 3 is itself greater than 2 raised to 2, and so on. Right? So if a is greater than 1, the basic idea is that the higher power will lead to a larger value of the output. So for m being less than n, what you can say is that right, so if a is greater than 1, then m less than n will also imply if m is less than n, then the corresponding we can say is that the value of a raised to m must also be less than a raised to n, and conversely also, if a raised to m is less than a raised to n, I can say from there that n must be less than n, assuming that a itself is greater than 1. So again, let's suppose this is an inequality, 2 raised to x square minus 5x is greater than 64. So then I can say that means that 2 raised to x square minus 5x must be greater than 2 raised to 6. But then again, bases are the same, so I can compare the exponents and the sign of inequality will remain the same. Right, so the values of x that we get are less than -1, or they can be greater than 6. So again, in exponential based inequalities, this is something which we want to keep in mind, that when the base is between 0 and 1, then if m is less than n, that will imply that a raised to m itself is greater than a raised to n. If I take an exponent on both sides, the sign of inequality reverses, and conversely, from such a statement, I can compare the exponents by saying that the sign of inequality will reverse when a is between 0 to 1. And if the base itself happens to be greater than 1, then the sign of inequality will remain the same. If m is less than n, then that will imply that a raised to m is less than a raised to n. And conversely, if a raised to m is less than a raised to n, that will also imply that m is less than n when the base is greater than 1. And for between 0 to 1, it will reverse. So let's look at these questions. For the first one, of course, we can simply say that the 1 on the RHS can be thought of as 3 raised to 0. So since the base are the same, I can equate the exponents, right? Which again reduces to a quadratic in mod of x. So from here I can say that mod of x could be either -2 or -3. And we've already seen that again mod of x cannot possibly be negative. So there are no real values of x from here. Right? Bases are the same, equate the exponents, you get a quadratic in mod of x. You get the values of mod of x as being -2 and -3, but both values are clearly unacceptable. So the answer for the first question should be null set. For the second question, it's basically more of an observation-driven question. So an observation clearly is that 3 raised to 2 plus 4 raised to 2 happens to be 5 raised to 2 by Pythagoras theorem. So clearly x square should be equal to 2. Right? So the solutions are for the second question are given by plus minus root 2. In the second question, of course, a thought could be that, okay, by observation, clearly when x square is equal to 2, the equation is satisfied. But how do you know that there won't be any other solutions, right? Or just to kind of take a simpler question, for the equation 3 raised to x plus 4 raised to x equal to 5 raised to x, by observation, of course, x equal to 2 is a solution, but how do you know that there aren't any other solutions? So you can actually prove that there aren't any other solutions, but for that we'll kind of have to go through to the idea of graphs. So by graphical manipulations, we can show that this equation will have exactly one solution. So in general, a point that we could note is that one basic observation that we can always one thing that we can always say is that any such equation a raised to x plus b raised to x equal to c raised to x, where a, b, c are positive values and a is less than b and which in turn is less than c, such an equation will always have exactly one solution. Now the third question is actually a kind of question which we've already seen in the chapter of quadratic equations. So an observation is that these two values are reciprocals of each other, because clearly when you multiply them, when I multiply these two values, I'm getting 1, right? So over here I can simply substitute root 3 plus root 2x as y. If I substitute root 3 plus root 2 raised to x as y, that automatically will make root 3 minus root 2x as 1 by y. So then you get a quadratic in y which you can solve and then back substitute to get the value of x. So one value of y is 5 plus 2 root 6. So root 3 plus root 2 raised to x is 5 plus 2 root 6, which is the same as root 3 plus root 2 square, again by observation. So one value of x is definitely 2, and the other root value of y is 5 minus 2 root 6. So root 3 plus root 2x is 5 minus 2 root 6, which is actually root 3 minus root 2 square, which is actually 1 upon root 3 plus root 2 square, because we already seen the root 3 minus root 2 is 1 upon root 3 plus root 2. So clearly x must be equal to minus 2 then. right? So for the third question, answers could be 2 or minus 2. Now the fourth question, we actually have to be slightly careful. If we just say that the 1 over here can be written as mod x raised to 0, and therefore x square minus x minus 2 equal to 0 gives us the solution, then the answer will be incomplete. So actually now the problem in this question is that the base itself has a dependence on the variable x, and you have 1 on the right hand side. So we'll have to take two cases over here. The first case is that mod of x itself is not equal to 1. If mod of x is not equal to 1, then the equation can be rewritten in this way. And now since the base is not equal to 1, since the base is the same, I can say that the exponents must also be the same, which gives me my roots as 2 and minus 1. Right? But out of these values, for this particular case, I'll have to reject minus 1 because I'm assuming over here that mod of x is not equal to 1. So that gives me a solution 2. So the first case gives me x equal to 2 as a possible solution. Now for the second case, suppose I assume that mod of x itself is equal to 1. Because if mod of x is equal to 1, then clearly the equation will be satisfied, right? If x is plus or minus 1, then you'll get some integral value over here, and the base of course is 1, so the equation is clearly satisfied. So that's why the values of x for which mod of x is equal to 1, that is plus and minus 1, both of these values will have to be included in your solution set. So these are again two solutions. So in this case, the final answer will actually be plus, minus 1 and 2. So there are three solutions. If you had directly just said that, okay, since this is equal to 1, I can just simply say that x square minus x minus 2 is equal to 0, and then you would have got two solutions. So in that case, the solution set would have turns out to be incomplete. So the reason why you're getting an extra solution over here was that because the base itself had a dependence on the variable, and the right hand side itself was 1. So it was necessary to take the case that the base on the left hand side could possibly be equal to 1. So now in the fifth question, again it's kind of similar. The base over here again has a dependence on the variable x. So two possibilities over here again would be that I can, if I assume that the base is equal to 1, I get the values of x as 4 and minus 1, and again both these values will clearly satisfy the equation, because again after that x equal to 4, I'll get 1 raised to 5, which is 1, and x equal to minus 1, I'll again get 1 raised to 0, which is again 1. So both these values are acceptable. And the second case of course would have been that the base is not equal to 1, in which case you would have said that mod of x plus 1 has to be 0, which would again have given you that x is equal to minus 1. Very specific, under this case you would have not accepted x equal to minus 1, but anyway x equal to minus 1 has been included in a previous case, so that will be a part of the answer. So the final solution set in this case again is 4 and minus 1, and again you have to be careful about this possibility of the base being equal to 1, because otherwise again if you had just said that the exponent should be 0, then your answer would have been incomplete. Now suppose this is a question. Now there will be some things that we'll have to kind of take care of. The first thing, of course, is that which of the values of x should definitely be rejected right away. So as you can see, there's a expression in the denominator over here, so that should not be 0. Right, so x can neither take the value 2, neither can it take the value 3. Then we should take the possibility that the base itself is not equal to 1. So if the base is equal to 1, then what will have to happen? So the base will be equal to 1 when x is equal to 2 or 0. So the first case that I'll take is, suppose so if x is neither 2 or 0, then the base is not equal to 1, and I can then therefore directly say that this exponent must be equal to 0, which gives us 2x plus 3 So we get the values of x as minus 3 by 2 or 0, right? So from 2 and 3, I get the solution as x equal to, so I'll actually have to take an intersection of 1, 2 and 3. Right, so x takes the value minus 3 by 2 and 0. Now 0 actually, x shouldn't have been 0, so 0 will have to be rejected. Minus 3 by 2 is not a problem. So one of the solutions that we get is x equal to minus 3 by 2. The second case that we can take is that x can either take the value 2 or 0. In which case, as you've already seen, the base will become 1, right? If the base becomes 1, then irrespective of the value of the exponent, the left hand side should become 1. But now and therefore you would have said that 2 and 0 both are acceptable solutions. But then again, if you observe over here, the first condition should have obviously been true, because 2 is not, if x is equal to 2, this denominator will become 0. So I'll have to now take an intersection of 1 and 4. Right, so from 1 and 4, I'll have to reject the value of 2, because again for x equal to 2, this denominator will become 0, which is not allowed. So therefore there is that solution 0. So this given equation therefore has two solutions, minus 3 by 2 and 0. One last thing that I just want to mention in solving exponential equations is something that you want to take care of, is that in solving exponential equations, a 0 raised to 0 form, if you ever encounter a 0 raised to 0 form, whenever you encounter 0 raised to 0 form, from the point of view of solving equations or inequalities, that will always be taken as an undefined operation, right? 0 raised to 0 is not to be taken as 1. When you're solving equations or inequalities, some value of x for which you have a term of the form, some value of the variable for which you have a term of the form 0 is raised to 0, then such a value has to be rejected, right? So So exactly in the way that we say that all those values of the variable for which the denominator becomes 0 have to be rejected. Similarly, if there is any value of the variable for which you have a 0 raised to 0 form, such a value also has to be rejected. So as an example, let's say this is your equation, x plus 1 raised to. Right, so now in this question, if I say that x square minus 1 is 0, then that will give me my values as 1 or minus 1. Right. But x equal to minus 1 again will not be 0, has to be rejected. Right. Because if you equate the exponent to 0, you'll get x as 1 or minus 1. But at x equal to minus 1, the base becomes 0, and therefore the equation becomes of the form 0 raised to 0, which we are considering to be not defined. So that's why minus 1 will be rejected, and the only answer over here is x equal to 1. You might want to consider the possibility that the base could be 1, which will happen at x equal to 0, but at x equal to 0, the power becomes minus 1. And again, 0 raised to minus 1 itself will not be defined. 1 by 0 is not defined. So that's why that x equal to 0, the base equal to 1 case will not occur over here. So this completes the 8th concept from your booklet, which essentially covers equations, exponential based equations and inequalities. Thank you.